Hello everyone and welcome back to another video. In today's episode in our series on number theory, we're going to continue our investigation of the prime numbers and answer one of the most basic questions that one can ask about prime numbers. How many primes are there? So let's jump right into it and start by proving a few preliminary theorems that are going to help us in our proof later on. So the first theorem that the book has us proving in our investigation of the prime numbers is theorem, in the investigation of the infinitude of the prime numbers, is theorem 2.32. And this theorem simply states for all natural numbers n, the GCD of n and n plus 1 equals 1. So all that it's saying is that consecutive numbers are relatively prime. So for our proof, we're just going to start very simply by letting n be a natural number. Then there exist integers x equals -1 and y equals 1 such that nx plus n plus 1 y equals 1. Now, if you recall from chapter 1, we were looking into different proofs of how linear Diophantine equations like this one relate to GCDs. So if you remember, theorem 1.39 that we proved shows that because this equation exists, you can write 1 as the sum of n times an integer and n plus 1 times an integer. This means that by theorem 1.39, the GCD of these two numbers has to be equal to 1. And that is our proof. So we've basically just shown that for any two consecutive natural numbers, their GCD must be equal to 1. They must be relatively prime. And then we'll box this off. Okay, so that's the first theorem. The next theorem that we're looking at is theorem... Oh, holy crap. That is crazy. Let's make it a normal brush and then shrink it down. I don't remember how big it was before. I'd imagine I'd do it relatively small, like 5. Oh wow, even smaller than that. Maybe it was all the way down. Not that small. Technical difficulties, guys. Okay, I think this is probably right. Yeah, okay. Theorem 2.33. So for this theorem, we will let k be a natural number. Then there exists a natural number n such that no natural number less than k and greater than 1 divides n. Okay, and then for this proof, this is going to give us kind of an understanding of some of the logic behind how we're going to prove that there's an infinite number of primes. So for this one, we will let k be a natural and let n equal k factorial plus 1. So this also means that n is greater than k. I'll use a colon here. Actually, yeah. Theoretically, I think I should probably use a dash. So n is greater than k. This is math, not English, so if I'm using punctuation wrong, don't come at me. So then, by theorem, (2.32), k factorial and n have a GCD equal to 1 because n is 1 larger than that factorial. Hence, n cannot be divided by any number less than k and greater than 1, since its only common factor with k factorial is 1. And k factorial is just the product of every single number below k. So if n did have a divisor that was less than k and greater than 1, it would also be a factor of k factorial. So that's why showing that this GCD is equal to 1 also implies that no natural number less than k and greater than 1 divides n. Okay, and that is our proof for that theorem. And let's box this guy off. Okay, so that's the second theorem that we're proving. And then the third theorem will be (2.34). And this theorem simply states, and this is getting very close to just being an expression of there being infinitely many prime numbers. But this will be another crucial step in our overall proof. Let k be a natural. Then there exists a prime larger than k. And this is essentially just a proof that there are infinitely many prime numbers, but the book actually writes this out as a separate theorem that we use in our proof of there being infinitely many primes. So for this proof, we're going to start by letting k be a natural number. And then we're going to suppose, for the sake of contradiction, that no prime is larger than k. Okay, so that's going to be our initial supposition, and now we're going to show that this leads to some sort of contradiction. So what we're going to do is let n equal p1, p2, ... pl plus 1, where this is the list of all the primes below k. And also know that this is the list of all of the primes in this situation. So we're supposing that there's no prime larger than k, and then this is the list of all the primes below k. So that would be the list of all the primes. So by the fundamental theorem of arithmetic, n must have a prime divisor. So pi divides n for some I in this set. Okay. Thus, the GCD of n in this product of primes is equal, or is greater than or equal to this prime number, which has to be greater than 1, since all primes are necessarily greater than 1. However, by theorem 2.32, n is 1 larger than this product of all the primes. So the GCD of n and p1, p2, dot, 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 pl equals 1. So we have a contradiction. Hence, there must exist a prime larger than k. Nice. Okay, so we've shown that for all natural numbers, there must be a prime number larger than it. I am crossing out my own proof. Let's not do that. Beautiful. Okay. And so for this last proof, we're going to bring it all together, and we're going to actually show how many primes there are. So theorem 2.35. There are infinitely many primes. Okay. So for our proof, similar to what we just did in theorem 2.34, we're going to suppose, or for the sake of contradiction, suppose there are a finite number of primes. Hence, there must be a largest prime. And we're going to let A be that largest prime. Note that primes are natural numbers. So since A is a natural number, by theorem 2.34, there must be a prime larger than A. So A is not the largest prime. Which is a contradiction. Therefore, there are infinitely many prime numbers. Nice. So this is the proof of there being infinitely many prime numbers. Okay, so yeah, so let's look at our train of logic here a little bit. So we started just by showing consecutive numbers have to be relatively prime. I don't think we actually used theorem 2.33. I think it could have been used in theorem 2.34 to make that a little bit simpler potentially, but it just kind of shows a similar line of logic by using a factorial plus 1 and then combining that with theorem 2.32 in order to show that to generate a new prime number basically, or to show that n can't be divided by any of the existing prime numbers. A very similar construction to what was done in theorem 2.33 was used in theorem 2.34, and then also combined with theorem 2.32 again, seeing that consecutive numbers have to be relatively prime. We saw that we could always generate a new prime number if we have a finite list of primes. There always must be some new prime number, and that prime number would be something that's contained in the prime factorization of n, where n is this product of primes plus 1, because those product of primes could not be in n's prime factorization because of this plus 1, because of theorem 2.32. So seeing this, we see that we can always generate when we have any finite list of primes, we can always generate a new prime. It always implies the existence of some prime not in that list. And then kind of just drawing that out, that shows that there's infinitely many primes. Anytime we try to bound the primes, there's a need for another prime. There's a need for another prime to be added into the list. Because we can generate a number that has to have a prime factorization by the fundamental theorem, but it has to have a factorization by the fundamental theorem, but nothing in that list, based on the way that the number was generated, could be in its prime factorization. And that implies that there needs to be an infinitely many prime numbers. It also helps explain why we proved the fundamental theorem first, because that was useful in showing that there must be infinitely many primes. Okay, so extending on this, or I guess, so this proof, this particular approach parallels Euclid's approach in elements. In book 9, proposition 20, Euclid uses a very similar train of logic, but the way he does things, let me see if I can show you. The way he does things is a little bit different, but this proof ultimately also shows that there are infinitely many primes. Now, if you're actually looking and reading this proof, you'll see that he does things a little bit different. He does things with measures, and the way he talks about numbers and talks about primes and talks about what it means for something to be divisible by something. It's very different from the way we talk about it, but it's essentially the same logic tied up here that he's using for proposition 20. And maybe at one point I'll make a video on this particular proof and some other proofs of the infinitude of primes, because there are a lot of different proofs of this. So I have this book, which I showed in my stream last week. But so Paul Erdos, he would talk about this concept of the book, which is where God maintains all the perfect proofs for mathematical theorems. And it was suggested to him that he create a sort of first approximation of the book. And that's what this ultimately became. Ultimately, it wasn't published by him, but he started writing on this, and then he died, and then this was finished. Later on after that and dedicated to his memory. But so this proof is like, or this book is intended to be like some of the most the most beautiful proofs of the most foundational theorems. And the very first entry in this book is 6 proofs of the infinity of primes. So in this, the first one that it shows is Euclid's proof, which is kind of the one that we went over here. I don't know if you guys can see that very well. Maybe I should just show this. Maybe I should show my actual screen here. So they have the 6 proofs of the infinitude of primes. And the first one is that Euclid proof that we looked at from before. That's very similar to this. And then there's other proofs using different types of primes. And there ends up being 6 proofs. Like some of them have more analysis-based proofs, and they're all a little different. So maybe at some point this would be useful to show. And I guess I'll show you Euclid's approach too, since you guys wouldn't have seen that. But yeah, so this one you'll see he's like using lines and constructions, and the way he talks about numbers and divisibility is a little different. But actually, if you follow the logic of his proof, it's almost identical to the sort of thing that we were doing here, showing that you can always generate the need for a new prime, which he actually in his book I think is what he labels as G, I believe. Let me pull that up. But sorry, kind of nerding out about like math history here, but I hope you guys find this stuff interesting. If you're sitting here watching this video, you might. Yeah, so he kind of uses that concept here where like A, B, and C are the list of the prime numbers that exist. E to D is the product of all 3. There has to be some G that divides it plus 1. You can see that little extra unit there. So then G would have to divide. There has to be some prime G, but G is not any of A, B, and C is his logic. So that shows that there needs to be an infinitely many prime numbers. And the way he states it is prime numbers are more than any assigned multitude of prime numbers. An assigned multitude would just mean like a finite list. So that's the way Euclid proved this. This was one of the early contributions to number theory, because Euclid was, yeah, this is like ancient Greece. I don't know if I have the actual dates. I think I do, probably do in here, but like this is like very, very ancient math. But yeah, so that's the proof of the infinitude of prime numbers. And then along with that, we can start making some connections. We can start extending this a little bit more and gaining an understanding of what types of prime numbers are there an infinite number of, and what is the distribution of prime numbers. And then this is where like more and more complicated math starts coming into play. But we're going to start by kind of looking into some connections that we can make and a theorem that we can prove about infinitely many prime numbers of the form 4k plus 3. So we're going to start by proving a preliminary theorem that we're going to use in our proof later. So this theorem is theorem 2.37. If R1, R2, Rm are natural numbers, and each one is congruent to 1 modulo 4, then the product R1, R2, Rm is also congruent to 1 mod 4. And this proof is going to be very quick and simple. So we're just going to let R1, R2, dot, 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 Rm all be natural numbers such that Ri is congruent to 1 mod 4 for all I in the set. And then in the future, I'm just going to refer to this as for all I. But for the first time, I'll just specify what exactly all I means. For all I in this set, or I guess we don't do that in this proof, but in the next proof I'll do something similar. Thus, by theorem 1.14, R1, R2, dot, 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 Rm is congruent to 1 times 1, dot, 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 times 1. Because basically what theorem 1.14 is saying is that in a product that you can always substitute something else that it's congruent to, and that the number of the other product is still going to be congruent to the original product. So this is congruent to 1 to the power m, which 1 to any power is just 1, so that product is congruent to 1 mod 4. Okay, so that is that proof. And then we're going to use that in a proof about the infinitude of primes that are congruent to 3 mod 4. And you'll see why it works for 3 and not for 1 in this proof. So theorem 2.38, there are infinitely many primes congruent to 3 modulo 4. Also known as or of the form so that means you can write them as 4 times some integer plus 3, basically. So, yeah. So for our proof of this theorem, we're going to start similar to these other proofs about the infinitude of primes. Suppose for contradiction. And in this video, you're going to really get a sense of how powerful proofs by contradiction can be. Contradiction. Especially for proving theorems that aren't of the strict form, like of a strict conditional form. You'll see that these contradiction proofs can be very useful, very powerful in just proving certain statements true. So suppose for contradiction, there are a finite number of primes congruent to 3 mod 4 So this would basically mean that all the other odd primes are congruent to 1 mod 4, so there's an infinite number of those types of primes, but not of these types of primes, which theoretically could be possible, but we're going to show that it actually is not possible. Let P1, P2, dot, 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 Pn be the list of these primes Thus, for all I, Pi equals 4 Ki plus 3 for some ki in the set of all integers. So now we're going to let q equal 4 p1 p2 dot 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 pn minus 1, which equals 4 p1 p2 dot 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 pn minus 4 plus 3, which equals 4 times p1 p2 dot 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 pn minus 1 plus 3. So we're seeing that q is also of this form for k plus 3, or for this number plus 3. Now, since q is not in this set, and q is congruent to 3 mod 4, q is not prime. Because this is the list of all of the primes that are congruent to 3 mod 4. Q is not in that list. Because Q is this product of all of them, and it just wouldn't make sense for Q to be part of this list, because it's 4 times that product minus 1. Like, Q is much larger than any of these P's. So by the fundamental theorem of scrolled up a little bit there. By FTA, Q must. Oh wait. Sorry. Okay, I skipped 2 lines. Okay. Because of that, Q is not prime. Additionally, one equals 4 p1 p2 dot 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 pn minus q. So p1 p2 dot 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 pn q equals 1 by theorem 1.39. Also realizing I could have just used the one that we proved earlier, theorem 2.32 for this, but same logic. It's still only one sentence. So since p1, p2, dot dot dot, pn and q equals 1 for all I, pi does not divide q. Because if pi did divide q, then this GCD would have to be greater than or equal to pi. Now, by the fundamental theorem of arithmetic, q must be the product of primes. Very basic. It has a prime factorization. Okay, and then since q is odd, since it's since it's congruent to 3 mod 4 and not congruent to 4, 0 mod 4, since q is odd and not divisible by any of the primes congruent to 3 modulo 4, Q's prime factorization must only contain primes congruent to 1 mod 4. However, by theorem 2.37, the one that we just proved, the product of natural numbers congruent to 1 modulo 4 must itself be congruent to 1 modulo 4. So Q is congruent to 1 modulo 4, which contradicts the fact that Q is congruent to 3 modulo 4. Just by the way we constructed it, it has to be congruent to 3 modulo 4, just because it's 4 times this product minus 1. Oh, actually, it actually wouldn't have worked to use theorem 2.32 up here, because it's equal to, because it's not constructed as the product plus 1. It's 4 times the product minus 1. It might have worked, actually. No, it might have worked in a certain sense, but because it's 1 away from it, so they are consecutive. But there's also that 4 in there, which would have made it a little bit weird. So I think it actually might have been able to work. Hence, there are infinitely many primes congruent to 3 modulo 4. And that is our proof. Okay, so that is that next proof. So what we've seen here now is that not only are there an infinite number of primes, there's an infinite number of primes that are congruent to 3 modulo 4, that have this certain congruence relationship, that are in this certain congruence group. Can this be generalized even further? It can. However, the proof of that is actually way beyond the scope of our course, but I'll just quickly express this theorem just to satisfy any curiosity that you may have. This is a Dirichlet's theorem on, and mind my pronunciation, but it's Dirichlet's theorem on primes in arithmetic progression. And this generalizes the principle that we just proved for 4k plus 3, explains why 4k plus 3 works. And basically it states if A and B are relatively prime, are relatively prime natural numbers, then there are infinitely many natural numbers k such that, or it says in the book, it says for which. I will play the semantics game. AK plus B, for which AK plus B is prime. Weird looking K there. So just for some brief examples of this, just the proof that we looked at before, 4k plus 3. Are there infinitely many primes of this form, 4k plus 3, that can be written as 4 times some integer k plus 3? Well, 3 and 4 are relatively prime, so infinitely many. Okay, what's another example? Well, let's look at like 5k plus 4. Well, 5 and 4 are relatively prime, so infinitely many. Now let's look at another example, 9k plus 3. Well, for this one, 9 and 3 are not relatively prime, so there aren't infinitely many. In fact, I think that 3 is the only example of a prime number that has this form, because otherwise it would be divisible by 3. I think every other example that you can come up with is divisible by 3. Okay, so with that in mind, there's one other last theorem that I want to cover, and this is probably the most, this is one of the more modern theorems about the infinitude of certain things in the primes, and this is talking mostly about, this is as recent as 2004 by still living mathematician Terence Tao. There are arbitrarily long arithmetic progressions of primes. So this is from Ben Green and Terence Tao. And what exactly this means, it basically means that for any natural number, we can find a prime p and another natural number a, such that p plus a, p plus 2a, dot, 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 p plus na are all prime. So basically, for any n that you want to choose, you can come up with some progression of numbers, of primes, that, like, of this form that are all prime. Start with one prime add and just add a n times, and every single time that number will be prime. Now, the longest example that I could find that was found so far is for n equals 26. And I can just show you what that example looks like because remember, there's an infinite number of numbers. So to get some of these longer strings, you need to go very high. You need to choose very large numbers. So this is the longest string. Let's see if I can zoom in a little bit. This is the longest string of them that's been found so far. And it's this weird construction. Like, this is the first prime, and then this is the gap number, which has this, like, hashtag notation that basically means, like, the product of all primes under 23. So this sequence of primes is the longest example of the green tau theorem. So all of these numbers are examples of primes. And the reality is we're only at 26. Like, there are strings like this that are like 1,000 long, 1,000,000 long, that exist somewhere within the set of all natural numbers that there are an infinite number of. So it's absolutely mind-boggling how someone could even come up with this theorem, much less prove it, and how we'll continue to generate these over time. But yeah, it just really shows that even though, like, as old as some of these questions are about the infinitude of prime numbers, like, the very first theorem was proven back in ancient Greece. But still, like, within the past, within this millennium, since 2000, there still is work being done on this. There's still so many things that are left to be discovered about prime numbers, about their nature, about just the infinite scope of them and the distribution of them within that infinite scope. So yeah, there's still a lot of work to be done in number theory, and there's still these problems, as old as they are and as, like, simple as some of the concepts are. Like, you learn about prime numbers in elementary school. You learn about greatest common divisors in elementary school. But as elementary and as ancient as some of these concepts are, there's still stuff continually being discovered on them, and there still are so many unanswered questions in the field of number theory. So yeah, I would recommend diving deeper. Recommend studying this more if you really want to. But I hope this can serve as a good introduction just into those concepts and help you get a appreciation for the scope and depth and just how interesting some of these questions are and how interesting some of this number theory actually is. But with all of that aside, we're getting to 50 minutes now. It's actually, as long as the video is, it is one of my shorter videos in this series, which is crazy. But yeah, we're 7 episodes in, and I don't see this stopping anytime soon. So thank you all for watching. Thank you all for all the comments and just saying nice things. Thank you for subscribing. Please, if you enjoy the video, go down and like. Go down and subscribe. Recently passed 500 subscribers, I think, in the last month at some point. So yeah, things are moving up, going well. And if you really enjoy this content, I have a Patreon link down below. I would really appreciate your support. I would really appreciate that. There's also a Discord where you can go ask questions. Or if I'm streaming and you want to call in, one of my viewers did that last week when I was streaming. I'll typically stream once a month. If you want to call in, talk, ask some questions, we can talk about anything. Really enjoy talking about math or philosophy or that sort of stuff. Theology obviously has been a piquing interest for me lately, but yeah, I appreciate all the support, guys. Thank you all for watching, and I hope to see you all in the next video. Peace.